Hi, welcome back to Math 520 Linear Algebra, and welcome to week 2. So last week we talked about a vector space and vector subspaces, and these were the objects that we defined and that we worked with. So now that we've internalized that, we're going to move on now to talking about bases and dimensions and the topics from chapter 2. So before I talk about the material, let's quickly discuss some course mechanics. The first thing is, as always, I've posted the readings and suggested problems to Blackboard. I'd like you to think about them, and your first discussion post is due Wednesday at 11:59 p.m. The second thing is one of the, actually for undergraduates, one problem, graduate students, two problems. I've now assigned from that week 1 suggested problem list that I'd like you to write up carefully and submit to Blackboard as a PDF file, and that is also due Wednesday at 11:59 p.m. I have two basic recommendations for how to construct this PDF file. One of them is to use software to write it. Something like LaTeX would be the canonical choice, but Word or Google Docs with their equation editors would also be fine. And then the other idea would be to write it out by hand and use your phone as a scanner. And I suggested some apps in the syllabus. Okay, so enough with the course mechanics. Let's say a few things about the course content. The first thing is, last week we really spent a lot of time thinking about vector spaces, the vector space axioms, and what makes a vector subspace. Now, the question then is, what is a vector space trying to have as its prototypical example? Right, so that's something that I would like you to think about a little bit this week, now that we've internalized the abstract axioms. I want you to turn this now into a concrete object in your mind. Okay, now in this second week, we're moving on to chapter 2, and the key things we're going to do now are really starting to use the fact that we're interested in finite dimensional vector spaces. So I would say that there are two really interesting things in this chapter as Axler presents it. The first one is an editorial choice that Axler made, and I'd like you to think about a little bit about why. So he talks about lists of vectors. He talks about a list of vector being linearly independent. He talks about the span of a list of vectors. And the interesting thing about a list is a list contains an order information, and a list allows repetition. Right? So these are two features that a set does not have. Now, many other textbooks on linear algebra talk about a set of vectors being linearly independent, or the span of a set of vectors. And that also makes sense. So here's a question to keep in the back of your head. Why did Axler talk about lists instead of about sets? And that's something I'd like you to sort of store in the back of your head. And when we start talking about the rank of a matrix and these various properties of a matrix, I'd like you to think back to this when we get there, and that's where this is going to pay off. Okay, the next key thing is that we have many theorems in this section, and they all circle around the same two ideas. And the two ideas are this. One, if I have a linearly independent set or list of vectors, and then I take some other vector that is not in the span of those, and I throw it in, I now get a longer list that is also linearly independent. Similarly, if I have a collection of vectors, a list of vectors, that is linearly dependent, then there's at least one of them that I can throw away. It's not clear which one, but there's one of them at least that I can throw away without damaging the span, so that the span stays as big as it was before. So these two facts get used over and over again in this section and the various ideas behind it. So in particular, I would like you to take a careful, well, first of all, I'd like you to try to prove those two statements that I just stated. See if you can come up with your own proof. And then afterwards, I would like you to take a look at the proof in Axler. These are specifically lemma 2.22 and theorem 2.23. And those really do an awful lot of heavy lifting in this chapter. So their proofs are worth taking a look at. But before you look at the proof, I would like you to see if you can come up with, at the very least, an argument for why it should be true. It doesn't need to be a perfect proof, but I do need you to wrestle with that idea in order to really appreciate Axler's proof once you read it.